literally wanted to. So
I forgot. I read my note. That was a talk. Now I remembered. So I was.
Oh no! Wait, is this when a man loves a woman very much?
You know,
very much about that time.
it would be an interesting talk. You know?
Oh, this is physics, not biology.
I probably, I probably would lose my job pretty quickly. So I've been pondering, all right,
Oh no!
and I feel like we're ahead of schedule now that they eliminated 3 entire units. Not quite. But I feel like we need a little bit more practice before we take this test tomorrow. All right. And I am a huge opponent against Monday tests. So I'm pushing it back to Tuesday. All right.
How would I have 3 tests on Friday to get moved
Yeah,
to Monday and Tuesday? That's crazy. Thank God I love teachers.
Okay.
Except for one.
Whoa.
So
I can take a guess which one it is.
Yeah.
So
I don't even dislike her teaching. I just don't like her.
I just feel like that's probably our best move. So we can go over the FET today. All right. That there was a lot of questions on that. So we're gonna go over that. Tomorrow I'll probably hand out like a review practice. All right. Going over each type of problem. All right. Horizontal, vertical, angular, UCMs. We'll go over universal gravity. Give a little review, and then maybe Monday we'll just do like a review game or something like that. Okay. I feel like we got a few days to spare, and I feel like that would help us out the most. That's the only talk I wanted to have. So unless you wanted to have them, yeah. I don't think anybody
We
did.
already went through it once. Don't
Yeah.
do that again.
Did you really have the talk in bio?
Do most people?
Not in bio with parents.
Oh, fair enough.
Do most
Sure.
people?
That was
In
embarrassing.
the profession of the man own firearms as he does?
Interesting.
No,
Okay.
All right,
Well,
Taylor, did you
we
hear
just-
that?
his profession doesn't have any.
What did you say?
Mainly,
him owning
we don't have a test tomorrow. So I decided to push it
Oh yeah, I did hear that.
All right, so I am going to go over the FET activity. So if you guys actually want to pull up the FET activity, that online activity, you can do that. Even if you turned it in, you guys can still pull it out.
Oh, I haven't turned that in yet.
That's fine.
Finished it yet.
That's fine.
Just turned it in.
What? No, we're going to go over it. You're good.
Okay.
Oh,
So you might want to get that out. We're going to go over it. All right, we're going to go over it real quick. Oh, no.
I'm done.
All right. So let's see. I want to pull up this. And I want to pull up activity. See what we're seeing. All right. So looking at this, the simulations, hypothesis, conclusions, I don't think there was any questions on that. The main questions came from the calculation. Would that be correct? Okay. So for Sim 1, calculate the period of Earth it goes around. If the sun had 1.5, so the sun had 1.5 times its mass, okay? Confirm your calculation, explain why. So what is the period of the Earth to go around the sun? Okay. So, I'm going to present my screen. Everybody can see. Beautiful. All right. So the sun times 1.5. Now, if we look at this, this is calculation number 1. Okay. So once I'm gonna write out my force of gravity. So force of gravity is equal to my G constant, M1, M2 over R squared. Right? Got that start. Okay? So my force of gravity, now this, we're gonna use Earth. Okay? Where force of gravity is equal to mass times acceleration. So what we're gonna do is we're gonna make these two equal to each other. We're gonna make that equal to that. Does that make sense? Because F of G equals F of G. All right. So mass of the Earth times the acceleration due to gravity is equal to G, mass of the Earth, 1.5 times the mass of the Sun.
Yeah, we forgot about that at first.
Over R squared. Okay. So when we do this, my mass of the Earth cancels my mass of the Earth. However, I'm just gonna leave it. It's fine. Okay. So mass of Earth on my thing says 5.972. 5.972 times 10 to the 24th times my acceleration is equal to my G constant, which is 6.67 times 10 to the negative 11, times my mass of the Earth, 5.972 times 10 to the 24th, times 1.5 times the mass of the Sun, which the mass of the Sun is 1.989, oh no, times 10 to the 30th. I made it work. Times 10 to the 30th, and that is all over the radius. So the radius, in this case, it's going to be the distance from the Sun to the Earth. Okay, and my radius is hot dog 147,100,000,000 squared.
That's a big number.
And that's how you would set it up. Do you guys get that far? Okay. From there, I got acceleration to be 0.009 three sig figs, so 922, somewhere around there. Meters per second squared. Yes.
Now I know this is kind of theoretical, but if you were to increase the mass of the Sun, like wouldn't the radius also decrease?
Mass is no.
No,
So like,
because
This-
like if you're
let's
fitting more.
let's say it's kind of like a radio when you stand by a radio and it automatically starts working a lot better. You never touched a radio and like it's staticky and then you get close to it and you touch it and it starts to work?
Yeah.
All right, same size,
Yeah.
different masses.
Yeah, but isn't the Sun like so tightly packed together?
I mean,
Possibly. I mean, if it were more, wouldn't it cause a black hole?
would it?
Maybe.
Black holes are usually it's pretty dense. I don't know how much more.
A lot more.
Does that kind of?
Yeah, that makes sense.
All right. So but that's my acceleration. All right. So now what I know is here's my Sun. Earth is going around. There's Mother Earth. Fun fact. What planet is closest to the Sun? Think wisely.
The Sun.
Yeah, you need to be
Mercury has a weird orbit. I think it's
1,000 times advanced.
Actually, it depends on the time of the year. Okay? Sometimes Mercury is the correct answer. Other times, Venus is the correct answer. Other times, Earth is the correct answer. Other times, Mars is the correct answer. Other times, Jupiter is the correct answer. Actually, I think it goes to Uranus. 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 I think it ends at Uranus.
Wait, did they really change the name of Uranus?
They did.
Are you serious?
I think it was always kind of like
Yeah.
that.
It's always
But
been Uranus.
just a fun fact, it changes on the time of year. All right, but anyway, so I know I'm going in a circle, so I'm going to use my centripetal acceleration, right? I'm going to use my centripetal acceleration. And my centripetal acceleration equation is v squared over r. Okay, v squared over r. So I know my acceleration is 0.00922 is equal to v squared over my radius. I'll write it out. 147,100,000,000. And we can solve for the velocity. Okay. The velocity I got was 36,820. Does that part make sense? You following so far? Now, the question said, what is the period? So I got to find my centripetal velocity, or my average velocity. Average velocity is 2 pi r over time, and that's what I'm solving for. Okay, I'm solving for time. So I know my velocity is 36,820 times 2 pi, my radius again, 147,100,000,000 over time. Okay. Now my time, when you solve for t, what do you guys get for t?
Like 36,792. Wait. No. Sorry, that was what I got for the speed.
I got you. I was going to say, I got
25 million, and then
25 million, 102,000, 25. What I got yesterday. Something like that. Somewhere around there. Everybody good so far? Now, that's seconds. All right, you got to convert that to days. All right, so divide that by 60. Divide that by 60. Divide that by 24. Overall days, I got 290. 290 days. Does that problem make sense? That was a lot of math. That was a whole page.
All these formulas on your formula tree.
I know the centripetal acceleration or universal gravitation. Let's see. Okay, universal gravitation's right there. All right, F of G. I'll show it on my paper. The universal gravitation's right there. Let's see. Centripetal acceleration is going to be on here. I don't see it though. Bless you.
Wait, it is up top.
Oh, it is. V squared over r. Okay. Centripetal acceleration. And velocity, 2 pi r over t. That one you're probably going to have to remember. I do not see that one. Yeah. I don't see that one. All right, so that's number one. Any questions on number one? Ready for number two?
Or I think the question on number one was why the calculations don't match the simulation.
Oh, explain why your calculations. So the simulation records around 200 days. The reason it doesn't match up is because the Earth starts to orbit into an ellipse, which varies the radius. So Earth, it's not a perfect circle. We don't orbit in a perfect circle. Okay. Number two, let's try this out. Hopefully this is going to start clicking a little bit. Okay. For simulation 4, calculate how far the satellite is from Earth's center. Okay, how far the satellite is from Earth's center. All right. So let's see. For simulation 4, did we get a time on that? That's what we found.
90-ish days.
So what?
90-ish days. No, it's minutes.
Yeah.
Oh,
90
minutes.
Yeah.
90 minutes? Okay, I was wondering. So in number 2, we had 90 minutes. Okay, let's convert that to seconds. So 90 minutes to seconds times that by 60 would be 5,400 seconds. So we got time. Okay, we have our time. So if we look, we know our velocity equation is 2 pi r over the time. Okay, right? So let's just kind of set this up. We have our time. Now we have to find the velocity. Okay? We have to find the velocity so that we can solve for r. Does that make sense? We're just like piecing it together. So to find the velocity, we have to use my centripetal acceleration equation, where centripetal acceleration is equal to the v squared over r. Okay? For acceleration, let's see, the acceleration we solved, or no, oh my gosh, I'm in the wrong spot. Don't listen to me. That was my bad. I'm jumping ahead a little bit. Not a whole lot of it. All right, so to find that, we're going to use my force is equal to my g constant m1, m2 over r squared. And use that. Okay, where my force is equal to mass times acceleration. Okay, so my force is mass times acceleration, g m1, m2 over r squared. Right? So I just converted this to this. We good? Now my acceleration, let's see. My acceleration is going to be equal to, let me make sure I'm doing this right. Okay, so we're going to have the mass of the satellite times the acceleration is equal to grams mass of the satellite times the mass of Earth. Okay, and that's over r squared. So if we actually look at this, the mass of the satellites cancel, right? If I have mass of satellite on both sides, they cancel. Okay, so I'm left with that. Okay, so my acceleration is equal to my g constant, 6.67 times 10 to the negative 11, times the mass of Earth, which is given up top. Mass of Earth is 5 5.972 times 10 to the 24th over my radius squared. I don't know my radius squared. Okay. So if we look at this, my acceleration, what's my acceleration equation? Oh, you can't see that. You guys got it, right? What's my acceleration equation? Velocity squared over r, right? So I'm transferring this into velocity squared over r. Okay? So now, if I look at this, what I'm going to do is I'm going to multiply both sides by r. Okay? So my r's cancel. This r cancels one of those r's. Does that make sense? Okay? So I'm going to rewrite this. I have velocity squared is equal to 6.67 times 10 to the negative 11 times 5.972 times 10 to the 24th over 1r. Okay? Let's see. My velocity equation. So what we're actually going to do is we're going to plug in my 2 pi r over t for this. Okay, so we're coming back down, plugging it into here. So I have 2 pi r over time squared. So I plugged velocity. Velocity's coming down. So v squared, right, is equal to all of this. I'll write it out. So 2 pi r over my time. I know my time is 5,400 squared is equal to 6.67 times 10 to the negative 11, 5.972 times 10 to the 24th over my radius. All right. So let's solve for this side first. All right. What is this side going to equal? What is this side going to equal? All right. Let me calculate. I didn't get this far. You got 2 times pi divided by 5,400. Square that number. So I got 1.35 times 10 to the negative 6th r squared. Is that what you guys are getting? All right. And that is equal to all of this. Okay. 6.67 times 10 to the negative 11. 5.972 times 10 to the 24th. Now, I have to divide it by r. Instead of divided by r, I'm going to get rid of that and multiply by r on both sides. So r's cancel. R times r squared makes that r cubed. And I can just solve for r now. So I have this times r cubed is equal to this times this. And that's my goal. I was trying to solve for r. What do you guys get? Anybody gonna plug that in? Anybody do this problem? Okay. This would have 3. So I got 6,660,000. So you guys again? Yay, nay. Anybody else get that? Awesome. So yeah, 6,660,000. That's our final answer. That would be in meters. That would be meters. Okay. Any questions on that? These are long problems, but it's actually really good practice because looking at some of the AP practice problems that you're going to be seeing, they're pretty long. Any questions on number 2? We doing all right? Are our heads hurting a little bit?
Yeah.
Just a little bit? I get that. I get that. Just think though, no test tomorrow. All right, let's keep going. Number 3. Number 4. Pretty easy. So last one. We got time. Last one. So for simulation 3, part 2, problem 2, part B. Use mathematics to explain why the moon moves, but the Earth does not appear to move. All right. So in this, we want to solve for the acceleration. So why does it appear that the moon moves, but the Earth doesn't move? Okay. So my force of gravity is equal to my G constant, M1, M2 over R squared. Okay. So if we just solve for this, the force of gravity is equal to, I'll write it out. 6.67 times 10 to the negative 11th times the mass of, doesn't matter, the moon's mass is 7.347 times 10 to the 22nd times the mass of Earth, 5.972 times 10 to the 24th over the radius between the moon and the Earth, which is 384,403,000 squared. All right, so what's my universal force of gravity? What'd you get? Okay, so I got 1.98 times 10 to the 20th. So you guys are getting? Yeah. Okay, so we solve for force of gravity. Now, that's the force of gravity. Is the force the same between the Earth and the Moon? The force between them? They are, right? They're both pulling the same. Okay? Now, what we're going to do is we're going to find the acceleration due to gravity on Earth and on the Moon. Okay? So let's do the Moon first. All right? So force is equal to the mass of the Moon times the acceleration. And then we're going to do Earth. So Earth is equal to F of G is equal to the mass of Earth times the acceleration due to gravity on Earth. Or, well, what we're solving. Or the acceleration of Earth. Okay, so force of G. So 1.98 times 10 to the 20th, which we just solved, is equal to the mass of the moon. The mass of the moon is 7.347 times 10 to the 22nd times A. And down here, it's the same thing, 1.98 times 10 to the 20th is equal to the mass of Earth, which is 5.97 G times 10 to the 24th times A. Okay. Point 0.00269. This one. Thousands. Point times 10 to the -5, so that would be 1, 2, 3, 4, 3, 3, 2. Thousands. That's what I got. So if we look at this, if we look at the acceleration, the difference between these two, is that what you guys are getting? Yeah. If you look at the acceleration, why does it appear Earth is not moving? Looking at these two numbers. Yeah.
It's moving a whole lot.
It's moving a whole lot less. Like, if we look at these decimals, it's practically moving 100 times less. Right? 50 times 5. Yeah, it's practically moving 100 times slower than the moon is. And that's why it appears that it's not moving. But in all reality, it is moving, right? Just very, very slowly. Does that kind of help out with question number 3? All right. Let's see. There should only be one more. Simulation 1, problem from part B asks how the force of gravity would change if the distance and masses of one would change. Okay. So looking at this equation, any questions on 3? All right, so 4 says, asked how the force of gravity would change if the distance and masses of one another changed. Okay, so force of gravity is equal to G m1 m2 over r squared. If the mass increases, if one of the mass increases, what happens to the force? It increases, right? So if mass increases, force would increase. If mass decreased, force would decrease. So those two are directly relation, okay? And if the radius in the denominator, I'm going to write this out again. If the radius in the denominator increased, we're dividing by more, which what happens to our force? It decreases. Okay, so these are inversely proportional. Okay, so mass and force are directly related. And radius and force are inversely related. And that's the PhET simulation calculation. Any questions on that? I know today wasn't a super exciting day, but I felt like it was probably good to go over this. All right. Now your test on Tuesday. Man, you probably won't see anything to this extent. You won't have a full page of calculations. All right. But I would be prepared for decent questions. Okay. Any questions on the PhET? Everybody good on that?
Cow on the dominant.
It is. It is. Do you have any questions, Taylor? All right. So, guys, we got about 5 minutes left. I feel like